Welcome back, folks. We're going to continue our discussion today of these SIR models, and we've been talking about them pretty extensively, and we've seen some really important stuff, and there's many videos for you to review. But we had this basic SIR epidemic model, which represents how a disease spreads over the short period, and we defined this basic reproductive number. And the basic reproductive number is defined in terms of the constants A and B. Remember, it involves these basic quantities of the epidemic, the number of contacts in the population, the probability of spread, and the average length of sickness. And it can be expressed in terms of A and B and N, which is the total size of the population. And we found that if R0 was less than 1, the disease is going to fade away, exponentially quickly, in fact, we saw that. And if R0 is bigger than 1, then there's going to be an epidemic. The number of infections will rise, at least in the short term. And in the homework, you'll see what the maximum number of infected people would be. So let's just look at the phase diagram for these again briefly. And you can see the picture we saw here previously that shows how the initial condition, remember if I start with no infected people, the initial number of susceptible and infected people must add to n. In reality, we'll start way down here where there's hardly any infected people, usually 1, and lots of susceptible people, almost n. And so in that case, you'll see an epidemic that has raising numbers until you get to this threshold, b over a, and then the infection will start to fade away. I didn't talk about it at the time, but another way to think about this is I've drawn this specifically so that b over a is less than n, right? In other words, I could rearrange that and say that an, putting the a on the other side and the b on the other side, an is bigger than 1. But if you remember, an divided by b, that's our R0. So this picture assumes that R0 is bigger than 1 precisely because of where I put the threshold. If the threshold was actually bigger than n, in other words, b over a was bigger than n, the threshold would be over here, and we would have none of this growing initial infection. And so this picture I've drawn here is specifically for when R0 is bigger than 1. This is the case where an epidemic occurs. The phase diagram looks different when R0 is less than 1, when we don't have an epidemic, because in that case, b over a is actually bigger than n, which is our R0 is less than 1. And in that case, every single one of these initial conditions, where I start along this line and the line hasn't changed, this is the number of susceptible plus the number of infected is equal to n, at the beginning at least, because eventually we're going to have some recovered or removed people. But every one of these initial conditions is going to take us down to 0 without going through an infectious phase. So this is the model that we had so far. This is an epidemic model. When R was bigger than 1, we had an epidemic, and the phase diagram looks like this. And when R is less than 1, we didn't have an epidemic, right? And so everything just fades away. The number of infected people just goes monotonically to 0. You just start declining in the Y direction. So this is our basic SIR model. We're going to generate it. We're going to generalize it to the case where the infection hangs around for a while, by which I mean that the infection is around long enough that it starts to matter that members of the population are dying and new people are being born. So we're going to include that in our model. Okay, so suppose we have a population that a disease sets in such a way that the disease is around for a long time. So long enough that the fact that people are dying by other causes and that people are being born it makes an impact on the population, right? So like the flu is an example of a disease that's like that. People die of the flu, but it's not an epidemic in the sense that that's the dominant thing happening in the population. That's one of the things happening in the population, but people are also being born, people are also dying, and so we need to take that into effect over the longer term. And that's the difference between an endemic, which means the disease is sort of established in the population and hanging around, and an epidemic where the focus is over a shorter period of time and the real thing that's happening in that period of time is the disease of focus itself. So we're going to think about an endemic disease, and COVID-19 may well become an endemic disease, a disease that just exists in the population over the period of years, which is not great, but let's see what our models might predict. So what I have here is the standard SIR model, right? This is just our SRI epidemic model that we've been talking about. But if I've got an annual birth rate of gamma, then I've got new people coming in. Sorry, that's not gamma, that's a capital lambda. You're probably used to the lowercase, that's an uppercase lambda. All right, so if I've got annual people coming in, then I need to increase the number of susceptibles by lambda, because lambda is the number of newly born people, and so I expect them to be susceptible to the disease. Now, it may be the case that the mother passes on antibodies, and that's a different level of disease, a different type of model that we're not going to talk about. We're just going to assume that every newborn baby is susceptible to the disease immediately. So the number of susceptible people is just increasing by lambda every unit of time, because this is the rate of change. But then people are dying, and I'm assuming that for the total population, sorry, I had a typo there. For the total population, the fractional death rate is mu. So in other words, for the total population, the death rate will be mu times n. But for any subpopulation, the death rate is going to be mu times that sort of part of the population. And so what I'm saying here is I'm subtracting a portion of each of these subgroups that are dying at the rate mu. So when I add that together, I've got the total subtraction from the total population of mu times s plus mu plus I plus r, just factoring out the negative sign. And you can see that if I add all of these things up, we're going to get these terms cancelling. We're going to get those two terms cancelling. These terms are going to add up to give us a total of, there's a gamma, sorry, a lambda, and then there's a total of mu times s plus I plus r, which is mu times n, because this is my total population. So this is mu times n. So this is the total population, right? So this is the rate of change of population. By adding these equations together, I find that the rate of change of population is increasing because of births, not surprising, and decreasing because of deaths, because the total death rate per fraction of the population is mu. So the rate of change of the population is the balance of those two things. What I'm going to assume is, for simplicity, because we like things to be simple, I'm going to assume that the total number of births exactly balances the total number of deaths, so that this is equal to 0, so that the population is constant, right? Because if the rate of change of s plus I plus r is 0, then the population n is equal to a constant value. And that's what I'm going to assume for simplicity. But that means taking a specific assumption about the birth rates, which is that they entirely balance the death rates. So let's put that together in the final endemic SIR model. And here's the final model, where I've replaced that capital lambda with mu times n, and everything else is the same. So we have people getting sick, becoming infected, then they're recovered, and then this last term in each equation represents a natural death rate, and this term represents births. So let's think about the graphical analysis of this model. Again, we want to be able to do a graphical analysis, which means I'm going to ignore this last term so that we don't have to worry about 3D, because notice that if the population is constant, then the number of recovered or removed people I can get entirely by knowing the total population and the current number of susceptible and infected people. And in fact, the R variable does not appear at all in these equations. N is a constant. And so I can treat it, as I did before, as a system of two equations and do a graphical analysis. But before I do that, let's factor these equations a little bit. I'm going to begin with this second equation, and I'm going to factor out an A times an I. You see there's an I in every term, and it might not be obvious that I care about the A, but I'm going to factor out the A and the I here, and that's going to leave us with an S minus, well, there's a B plus a mu divided by A. And the reason it's useful to write it that way is we'll be able to easily see what the equilibrium points are. When I is equal to 0, or where S is equal to this combination of things. B, remember, is our recovery rate, and mu is the natural death rate in the population. And then what's left in the other term, I'm going to factor again a similar thing. I'm going to factor an A times an S out, and I'm going to write it in this kind of, it looks maybe complicated way, but if you multiply that out, you'll see that it's exactly the same equation as I have up here. But again, we have a factored form where we can see that there's two special places, something that makes ds dt equals 0, well that's s equals 0, just like over here, I equals 0 makes the rate of change of I 0, but also so does s equals b plus mu over a. And on this side, this is no longer just a constant value, this will actually be an entire curve, and it'll be the curve along which I is equal to mu over a n over s minus 1. And if I has that value, then ds dt will be 0. Let's look at the equilibrium values. So working through this equation, if you look at the first one, if I make s equal to 0, and remember here that I've got a bunch of constants, the a, the b, the mu, they're all positive. Did I leave anything else out? The n, the total population. These things are all positive numbers. I'm assuming none of them are 0. And so I want to find these equilibrium values, and I'm going to do it by saying, okay, the first equation, s could be 0. Well, let's actually start with the second. Let's take this I value. The I value is 0. So the SI values for equilibrium values here. When I is 0, if I go to this equation, then I get a 0 here. This quantity should not be 0 unless s is equal to n, and that's a very special choice for s. So what I actually would be forced to have is either s is equal to n. So if I is 0 here, then I can make this factor 0 by choosing s to be n. So this is n comma 0. Or I could make it equal to 0 by choosing s equal to 0. So we've got two equilibrium coming out of the choice that I is 0. And then if s has this choice, b plus mu over a, plugging that in here, plugging it in the front will give us a non-zero number. So the only choice is that n has the value that you get by plugging in the I value when s is, what was it? B plus mu over a. So I'm plugging that in here, and I did it really ugly way. This is some value, right? You can simplify that to get something like this. So there are 3 equilibrium points, and we can do a graphical analysis. Okay, so here's the 2 differential equations we're using. Here's the general setup. What we have is the line I plus s is equal to 0, because if we assume there are initially no recovered people, the constant population tells us that everybody's either susceptible or infected, so we lie along the line, I plus s is equal to n, which is this line. We also have the 2 special kind of lines where s is equal to 0, along which s does not change, and I equals 0, along which I does not change. So when s is equal to 0, we're along this line, and s does not change, which means we're either moving straight up or straight down. So we have a bunch of trajectories here that either move straight up or straight down, and so s is equal to 0. In this case, we're going to get a negative, right? Because s is equal to 0, this is a positive term, that's a positive term. So I is decreasing in this entire region here. So we're going to be moving down towards, remember there was an equilibrium point at the origin. Now, when I is equal to 0, this whole term is 0, so I is not changing. And so now we've got this quantity. And to make sense of this, we need to plot the line along which I is equal to that ratio, n over s minus 1. Right? And this, you can think of this, I is playing the role of the x-axis. This is something like some constant out the front, 1 over x minus 1. So this is the graph of 1 over x moved down 1. When s is equal to n at this point, I is 0. So this curve is going to be a 1 over x graph that's moved down 1, and it passes through. Well, let me make it a bit more easy to sketch this. This is a 1 over x graph that's going to go down and pass through there. All right, so there is a special value. That was one of our equilibrium points, right? That's when the line, the curve given by this equation and I equals 0, where they intersect. And so we get a curve that looks something like this. Now, there was one other value of s that's important. There's this s value, b plus mu over a. So I'm going to draw the curve. Here it is. Here's the curve where S is equal to B plus mu over A. And to have drawn it like that, I'm assuming that that's actually smaller than n. So I'm assuming that B plus mu over A is less than n. Or put that another way, AN over B plus mu is bigger than 1. And that might look familiar from the beginning today. That's what I'm going to define R naught to be for this model. This is our basic criteria for an epidemic to occur. So just by rearranging this inequality, I'm getting this value, AN over B plus mu must be bigger than 1, and I'm taking that to be R naught. I'm defining it from this idea, right? And once I've defined it from this idea, because I want the line to be here, I want this to be the place where S is equal to B plus mu over A, because if it happened over here somewhere, I wouldn't get the interesting dynamic. So the third equilibrium point is where those two intersect. So the point of all of this is along this complicated line, ds dt is equal to 0. Along this line, where S is equal to B plus mu over A, di dt is equal to 0. Right? And so we can work out what's going on here. So when you're on this line, I is not changing, so we're moving directly left or directly right. So we look something like that with our trajectories. When I'm on this curve, S is not changing, so I'm moving straight up or straight down. The S value is not changing, right? I'm moving straight up and straight down in the Y direction, in the I direction. So there's how my trajectories are going to behave. Now, we've got to look in these 4 little regions that you can see there to find out what the other variable is doing. So let's look when the S value over here is less than B plus mu over A. So everything to the left of this line is where S is less than B plus mu over A. And so the IDT is negative because this is always positive and S is smaller than the thing you're subtracting. And so the rate of change of I is negative. So I is decreasing everywhere to the left. I is decreasing to the left. I is decreasing, right? All of these trajectories are decreasing. If you go to the other side, I must be increasing. So I is increasing over here. So any trajectories I draw over here have to be increasing. Now let's think about the same idea with this curve. Here I've got when this quantity is equal to I, in other words, I'm on this line, then S is not changing. But what is happening to I? Well, we already know that. What about if we're above the curve? If we're above this nice curve, then I is being subtracted by something, from something, but I is bigger, and so this will be negative. So S, when you're above the curve, S will be decreasing, so we'll be moving to the left. If you're above the curve, you're moving to the left. Same argument, if you're below the curve, you're moving to the right. So our trajectories must look something like this. How do we fit trajectories into that? Well, think about starting along this curve, because this is where our initial condition lies, right? Our initial condition has to be on the curve I plus n is equal to 0, because initially those two things together add to n. Sorry, not 0, to n. But if I'm in this region, which this line is, then I must be moving left and up. So moving left and up, my curve has to go something like this, left and up until I get to that line where I have to be moving flat. But then by the time I get to this line, I have to be going down. And then here I'm going down and to the right. But by the time I get to this line, I have to be going left. But by the time I get to this line, I have to be going right up. And then, so you can see that my trajectories are going to circle into that point. So any trajectory here is going to go up for a while until it's going down, until it's going straight down, until it's twisting around. And so as I try to build these trajectories, starting over here, I'm going down. These trajectories are all going to be, here I'm just going down and to the right from the beginning, so it's going to look something like that. So all of these trajectories must somehow be twisting in towards that central point. In other words, we have a stable equilibrium right there at the center, which is complicated to write out, but it's this point here where S is B plus mu over A and whatever that I value was. So we've got a stable equilibrium. And you can see what's happening. I'm twisting in. So initially, let's think about one trajectory here. The number of infected people increases for a while. It increases until I get to here, at which moment the number of infected people starts going down. And it goes down for a while, but then eventually the number of infected people starts going up again. The number of infected goes up. It doesn't go as high because last time I was over here and now I only get to there before it starts decreasing again. The number of infected is the y-axis, right? So I'm going down and up and down and up. And each time I go through one of those oscillations, the number of infected people is not as big as it was the time before. And this is typical of what happens with an endemic disease. The first sort of hit of the disease is the max, sort of has a big number of infected people, and after that you get echoes of that disease happening, but each subsequent maximum is not quite as big as the one before. So looking at a slightly nicer version of this phase space portrait, you can see here that the oscillations are settling down on a fixed point. And I've graphed it here against time. So we've got time and SIR, and you see we start with no infected people. We're going to have this simulation started with one infected person. And so almost everyone in the population was susceptible. And then what you see is an oscillation. You see that there's a maximum, this I is down here, there's a maximum in the number of infected people, and then that falls off. But then you get a second maximum. And that's the idea of here's our first maximum in the number of infected people here. So if I think about this as our starting point, we get a first maximum in number of infected people, and that circles around, but then we get a second maximum in the number of infected people, and then it circles down, we get a third maximum in the number of infected people, and you can see those maximums happening here. And what's happening is that the disease is kind of dying out, but then new people are coming into the population, right? We have a birth rate here replacing people who are dying. And so those new people are coming into the population and making a population of susceptible people in the population again. And so as the number of susceptible people slowly grows, as old people are dying off and new people are coming in, the proportion of susceptible grows, and you can see that here in the blue line. We have a minimum of susceptible people, but then the infection has kind of died out, and then over time the number of susceptible people grows to the point where the disease can take over again. And so at the top of this growth in the number of susceptible people, the disease kind of takes a hold again and causes the number of susceptible people to shrink. But then once the susceptible people falls below a limit, and we know what that limit is, right? We've talked about that for the other model. Once we fall below a limit, the epidemic kind of dies off. The number of infected people falls, but that means that the number of susceptible people is going to grow again because new people are coming into the population. And this happens again and again and again, and the strength of these oscillations kind of die out. But what we get is a stable equilibrium. Right, we have a stable equilibrium where the disease hangs around in the population at a roughly constant level over time. And this is very different from what we saw in the other SIR model, the epidemic model. This is an endemic disease, and you can see the disease hangs around in the population because this long-term level at which I is at, and you can see it here. Here's our, let's call it I sub infinity. That long-term value is not zero. So over time, you've always got a certain percentage of the population who have the infection. And every now and then, a kind of small epidemic pops up, and you can see that here, although the strength of them dies off over time. That's what our model's predicting. That was the case where the basic reproductive number was bigger than 1. In other words, this point is to the left of n. What happens if that point's to the right of n? Let's quickly sketch that. So in this case, we're going to take the basic reproductive number less than 1, and just rearranging that, what that means is that b plus mu over a is going to be bigger than n. And if b plus mu over a, that's this value here, if that's bigger than n, then when I draw the diagram, then b plus mu over a is going to be out here. So it's going to be outside the region, right? It's outside the region where I plus s equals n. Our initial conditions have to be on this line, and we have to end up with a trajectory that happens inside this triangle down here. So we're never going to reach this fixed point. So the value of s is always going to be smaller than this because our values of s are always along here. They're always going to be less than n between 0 and n. And so S is going to be smaller than that value, and so this quantity is always going to be negative. So I is always going to be decreasing, and that means that the disease fades out. So we just have to work out what S is doing, and what S is doing depends again whether I is above or below that curve. So regardless of where we are, I is decreasing. So all of our trajectories are going straight down. On this purple curve, I is equal to this value, and so S is not changing, and so we're literally heading straight down as we pass through this purple curve. If we're above that curve, then that value minus I is bigger than that value, and so S is going to be decreasing. So we're going to be moving to the left. And if we're below that curve, we're going to be moving to the right. So these values are going to move to the right. Everything moves down, but in this region we go left, and in this version we go right. When S is equal to 0, S doesn't change, and so we move straight down the I-axis here. And when I equals 0, I is not changing, and S is going to be positive, and so we move to the left. The rate of change of S is going to be positive, and so we move to the left here. And you can see that we have a fixed point there. We still have a fixed point in the middle here somewhere. Well, no, the fixed point is going to be actually down here, the other fixed point. So kind of sketching trajectories here, starting on this curve, we move down and to the left until we hit that purple curve, at which point we're moving straight down, and then we're just moving to the left, and we have to be going like that somehow. So the trajectories here all have to have this general shape. So in this case you can see the disease dies out and the number of susceptibles goes to n. How do we make sense of that? You can see that every one of these trajectories takes us down to this stable fixed point down here where I is 0 but S is the entire population, right? This is the stable fixed point n0. And the way to interpret that is, well, the disease dies out because the number of infected people go to 0, because the basic reproductive rate is less than 1. That's our requirement for the disease to die out. But then people are being replaced. The whole population is n, but they're not the same people. There was a group of removed people, but eventually they die off. So the disease becomes like a memory because nobody alive has ever had it because it died off, and then the people who had encountered and recovered from it have died and been replaced by people who might be susceptible, but they've never encountered the disease. So you can see in this figure, I've started with 50% of the population with the disease. And the disease just dies out because, as we saw in the previous sort of calculation, when R0 is less than 1, the rate of change of I is less than 0 for all time. So the disease is just decreasing in size. And again, we're plotting this against time. And the Phasespace diagram tells us that all of the trajectories are going to take us to this point where there are n susceptible people and no infected people. And that's exactly what you see here. The number of susceptible people, this blue line, goes eventually to 100%. The number of recovered people, you see the number of recovered people here, it zooms up. You can see it gets close to 100%. In other words, at some point early on in this disease, everyone has it, right? The number of recovered people is almost 100%. What is this? Let's say that's 95%. So it looks like if you start with 50% of the population somehow get this disease, at the beginning, you're going to quickly get to the point where most of the population has the disease, but then that percentage is going to drop off because those people are being replaced. That population is going to drop off, and the number of susceptible people is going to go to n, precisely because the number of infected people goes to 0, and at some point there are no more people who have the disease anymore. So there's no disease left in the population at some point. So although you have people who recovered, eventually you'll have nobody left in the population who has ever encountered the disease. So the entire population will be susceptible and no one will be recovered because the people who had the disease have died and been, replaced with a new population who are susceptible again. So hopefully this gives you some idea how an endemic disease model behaves and how this basic reproductive number, although it looks slightly different here because we had to take into account in our previous SIRI model, our basic reproductive number looked like that. And what we had to do, remember this is the recovery rate, what we had to do is essentially correct the recovery rate for the people who were dying of other causes. And that's what this thing in the denominator is really doing. So either way, there is a quantity in the model that represents the basic reproductive rate, and it's key to whether the disease becomes a thing or whether it dies out in the population. Thanks again for tuning in. I hope this has been interesting.